conversation.
So Erica, again, sends her regards. She is actually teaching summer school for outreach students, and that was another consideration here back at Brown with Lauren Joswiak. So they're working with a whole series of high school students, about 25 of them, I think, and they're incredible. Okay, so she's doing her service. So Erica's been working on pyroclastics, and it's turned her attention to this huge pyroclastic deposit. We have an end member, as I tried to say this morning, of like tiny little cones all the way up to huge volcanic outbursts, etc., producing regional pyroclastic deposits. And we know, of course, that lunar volcanism is very extensive in this whole region here. We have a total variety of features, from these lava flows to these small cones. This is 2 kilometers here. This is a few hundreds of meters across. And then we have things like these Grottyson domes, which are more viscous domes that are like 20 kilometers across, maybe 1,200 meters high. So this is an interesting configuration. But we also have these big complexes. So western Okeanos Procolarum in the western Maria, okay, there are 3 of these. There's the Rumker Hills in the north. In the intermediate areas is the Aristarchus Plateau. These are topographic maps from Lola. And then we heard earlier from Brian, the Marius Hills, for example. So this thing is really interesting because it's not a volcanic construct. It's a highland plateau, but it has a combination of features on it. They're absolutely amazing. The Cobra head, this vast sinuous rill that extends out here, a multiple nested sinuous rill. And so that's what we've been studying in detail, because there's evidence there for extensive pyroclastic eruptions of an end-member type that we don't see anywhere else on the moon. So what's the geography here? So this is the crater Aristarchus. This is Herodotus, a much more highly degraded crater. And this is the edge of the plateau, of the Aristarchus Plateau. And this is Cobra Head. Cobra Head was named from Earth-based telescopic observations because, in fact, it looks like a snake's head with a tail extending off kilometers wide, as you can see here, out to the edge. And then it's embayed by younger lavas from Okeanos Procolarum. Nested in the middle here is a second very sinuous rill. So this is a sinuous rill that formed and then had maybe a later stage of the eruption that flowed down the central part of the rill. So how do you get this thing, and what does the data tell us, this new data from LRO, LOLA data for topography, and LROC data for detail resolution? And can we explain the presence of the major volcanic features on Aristarchus with a single formation mechanism? It's covered with pyroclastic deposits, but we don't see hundreds of vents. We only see one really big vent and some other sinuous rills. So can we explain all that with a single mechanism? So this is the largest pyroclastic deposit on the moon, 50,000 square kilometers, and it's low titanium, glass rich, 20 to 30 meters thick, and we can tell that from impacts that have excavated material from below. Maps have been made of this. A number of people have worked on this, referenced there. So the question is this area here the source of all this stuff, or is it not? Okay, these are critical questions. And what's the source of something this big? What's the mechanism for formation? Now, as always, when you have something this interesting, there's something that comes in and messes everything up. That would be the crater Aristarchus, a very fresh crater, and you can see the ejecta from that coming over the area of interest here. So that confuses things somewhat, but you can kind of subtract out secondaries and ejecta deposits and map them and take them out. And when you do that, you can produce a topographic map, which really gives you the idea of the underlying morphology. And it's really kind of dramatic here, okay? If you take a look, this is Cobra Head, and you can see the small sinuous rill going down the middle here. This is quite deep, and it's really prominent. And just to the south of it is this large mound, this cone here, which is really high. There's a nested rills, this irregular, and then there's another couple of them here between Herodotus and Aristarchus crater here. So this is quite big. We're talking almost 1,400 meters high. You can see here, and it's about the same size, if you will, as the Grottyson dome. But it's not a viscous thing. It's very fluid. These are obviously basaltic mineralizing composition. So Eric has been trying to think through how this kind of thing can form using the work that Lionel and I have done on theory of ascent and eruption. We take a look in more detail, and we see, in fact, in these areas here, evidence for these kind of satellitic craters. So this is the crater, the large crater. If we blow this up, we see lots of little pits and mounds, not pits, but lots of mounds across the surface here. They look like small vents, okay, small mounds of material. And then when we look at the slope data, we can see the relationship of these things, and there's several what we call individual eruptive phases in here, apparently, or individual eruptive features. So how are these things all related? Well, if we go back to dike theory, you can see that these are fairly well aligned along here, that we have the main vent itself, and we have this dome, and then these other two, and perhaps this represented the surface manifestation of a single dike. And what would happen if we had a dike that produced something this large? We can go back to, in fact, terrestrial volcanology and take a look. This is not 1,6G and no atmosphere as on the moon, but the way these things work give us some idea of how this mechanism might occur. So here is from a paper Lionel and I did in 1989. We looked at the Hawaiian eruptions, of which this is likely to be the same type except on the moon. And there's a couple of things to note here. First of all, you can see that the spread angle is really important here, okay? The width of the fountain is really important. That's governed by a number of things, the atmospheric pressure, but it's also governed by the shape of the vent. Now, one thing you'll see is that there are places which we call optically thin and optically thick. So what does that mean? Okay, so this is an optically thick portion of the plume. It means that the fragments are very close together. They're not cooling very efficiently because there's not a lot of atmosphere in there to let them cool. And not only that, when the little bit of air that is in there is quickly heated and adds to it. But you can see as you move away and the particle density becomes lower, the color changes. So that when you look at the outer portions here, it's dark. That's just simply, the optically thin as opposed to the optically thick portion of the fountain. So this is telling you how these things work. And there's also a component we don't have to worry about on the moon, which is the wind. You can see there's wind profiles can have an effect. That's what's going on here. It's all blowing off in this direction because the wind is doing that. But the key point here, this is the optically thick part, this is the optically thin part. And the shape of that is due to the spread angle. Now, much of this comes and falls back down into the vent itself, and that's what causes the lava flows that go out. They're a little bit more degassed than they would be if they hadn't vented like this. So we can take a look at this and think about what happens if you had one of these on the moon. Although the ejecta would be dispersed quite more widely, nonetheless, the principles are the same. If you have essentially pyroclastic accumulation rate going from slow to fast and mean pyroclastic temperature going from cold to hot, obviously, if you have brittle cinders out here, where do they form? They form in the optically thin part of the cloud, okay, where things are cooling and falling down, and by the time they hit the ground, they're cold enough so they just pile up as cinders. On the other hand, if you're out in this area here, where the fragments are hot and the accumulation rate is high, which is in here, just like something here, you'll produce a lot of material building up, and it produces rootless flows and other types of features that can pile up and create pseudo-volcanic structures, but are really just piled up welded tephra, if you will, welded clots like you see here producing rootless flows. So we kind of have an idea here. We'll get welded spatter, we'll get rootless flows, a whole series of things that might help to explain some of the topography we see, the unusual morphology on the moon. So when we go back here, the models that Lionel and I have done would suggest that if you have a wide enough dike here on the wide side for the moon, this will, in fact, in its initial stages and throughout the significant first parts of the eruptions, have sufficient pyroclasts, so they pile up in the area so efficiently that actually you're creating a thermal erosion of a pond in here, okay? And then thermal erosion as this material goes out, and it lasts so long and is so turbulent that it's actually transferring heat to the substrate and creating a major sinuous rill. If that's the same context, you're getting a lot of lower optical depth material here at which you will pile up a significant amount of material around the outside and indeed have a two-phase kind of flow, which is the pyroclasts that are going out regionally and those that are piling up from the optically dense portion of the cloud around the dike and the vent. So we've done some calculations on this, and it seems like this kind of model could indeed account for the kinds of things you see in the Aristarchus Plateau, both the regional pyroclastic deposits and the local pyroclastic deposits and the sinuous rill. So the dike propagates to the surface, initiates along a dike, optical density determines a volcanic construct, okay, and then a vent centralizes to the Cobra head, and then effusion continues and decreases, and that's when the flux is sufficient so that for the nested rill to form in the latter stages of the eruption. So we think we have a model for this, but we're testing it out. It's possible that, certainly this is an end member, it's a larger sinuous rill, biggest pyroclastic deposit, and the most unusual satellitic cones we've seen anywhere on the moon. So this is probably an in-member type of eruption, and we're looking at that to tell us something about the range of activity on the moon and why at this one place we have this unique in-member dike emplacement event to produce the Cobra head, the cone itself, and this unusual sinuous rill. So we think that's a starting point, and now we're testing this model in detail. Thank you.
Any questions, Jim?
Everybody's on the 9 o'clock flight.
Okay, I'll start off.
People are asking themselves, why did I book the 9 o'clock flight? Right?
I can't remember if you mentioned it, but what is the ages of the deposits?
Yes, so these are in that same period of time. So it's kind of hard to date these because we don't have a lot of lava flows. But given the stratigraphy, we know that it's pre the later Procalarum flow. So it's in the major phase of lunar activity from about 3.7 to 3.5, somewhere in there. And
do you think that they all came from the same events? They're all sort of the same age, or?
The model accounts for both the very high fusion rates to produce the spatter from the optically dense part of the cloud, the accumulation rate to create the Cobra head depression, and the flux and duration of the eruption to get the sinuous rill, and then in the optically thin part of the cloud, that will be what dispersed out to produce the regional pyroclastic deposit. So it can account for it, but we have a lot of work to do to prove that.
One behind you as well.
Okay. So if this deposit was formed during a very volcanically active time period in the moon's history, do you have any thoughts about why we don't see features this large in other places on the moon?
That's a good question. So why don't we see features of this size in other places on the moon? Well, the simple answer to that, which is not really an answer, is that there is a spectrum, and this is one end of the spectrum. And so if it's a frequency distribution of like dike widths, then this is extreme. So that idea would minimize the possibility of having as many of these as we do other features. It's possible that these occurred below the Maria. The reason we see this is because it's sitting on a highland plateau. So it could be a preservation effect. Generally, with Grail, we're starting to see features in the subsurface of the Maria that some people on our Grail team think are lava tubes, but they're huge. And I'm thinking there may be something, that some of these things may be manifestations of this sort of thing below the Maria, where you wouldn't expect them to be preserved. So my sense is that they're going to be rare, but hey, maybe the end member is also buried, and maybe these are more towards the median than we think. It's a really good question.
So Jim, just a question in general. What is the last epoch that we see volcanic activity on the moon? How long ago did it stop?
Okay, so that I think the best established young date is from impact crater size frequency distributions, and it's at about 1 billion years. And then there's a question of these irregular Maury patches, which have been dated to less than 100 million years, which is like today geologically. My opinion is that that's probably not the right date, that they probably date back to the earlier periods, but boy, that's, we got a lot of talking to do about that. So I would say most people would agree about 1 billion years ago is the latest. And again, it's consistent with the overall thermal evolution of the moon. It's small. The radiator effect, you're going to cool the lithosphere thickening. We know from seismic data it's about 800 kilometers thick. So, it's really that. The thing is, with time, you're not just making it harder to get the lava out, but you're producing less because it's cooling. So it's kind of a double-edged effect. So it's reasonable that it's about 1 billion years from thermal models, but then there's a little bit of circular reasoning there. That's why this IMP thing is so exciting. If it's 100 million years or less, Jesus, that's incredible. I don't think anybody knows how to handle that.
All right, great. We'll end there and move on to the next talk.